Hi, everybody. It's me. It's really me. I'm not just a voice floating in space. I want to try this on Zoom for today and see how it goes. Somebody else wants to say hi right now, too.
Hi.
Yeah, it's Griffin. And it looks like Frodo right behind me is going to be in for the lecture as well. So what I'm going to do now is I'm going to spare you all my face and I'll take it off. But I want you to know that I miss you guys and I'm really here. Okay, so here we go. Let's get to today's lesson. It is sampling distributions of proportions. So yesterday, we covered the central limit theorem. Another name for the central limit theorem is called the sampling distribution of means. All right, this is the sampling distribution of proportions. So what I did was I made a couple examples here. Data can be collected and displayed as means, and here they are right here as means. What's an example of data collected as means? Well, how about collecting the number of hours that people sleep per night? Data can also be collected as proportions. And what's an example of that? Proportions, fractions, percentages. The percentage of time per day you're doing your homework now in isolation versus when you weren't in isolation or in a different world for a temporary period of time. So let's talk about the populations of each. All right, so for means, we have dealt with this before. The shape of a population of means can be varied. It could be normally distributed. It could be skewed left. It could be skewed right, uniformly distributed. It's varied. The size, therefore, is also varied. The mean is mu. Variance, sigma squared. Standard deviation, sigma. For populations of proportions, okay, the shape of a distribution is binomial. And why? Think of fractions. Think of percentages. 1/2 of the time a coin can flip heads. 1/2 of the time the coin can flip tails. All right, heads or tails, true or false. It's binomial. We're going to think of that concept, and because it's binomial, the size of that population is usually infinite. The mean of this population, this is where things get a little different. Instead of using the Greek letter mu, we're going to use the letter P for the mean of a proportion. And its definition is the sum of all the x's divided by n. Sounds like the mean, doesn't it? Or the mu, doesn't it? It is. It's a fraction, though. The variance is still going to be written as sigma squared. Okay? Now, binomial populations for means are usually n times p. We'll get to that in just a second. But here I just see that the mean is p. Where did the n go? I'll talk about that. The variance was, instead of n times p times q, which is what it was for means, it's just p times q. Where did the n go? And standard deviation is still sigma, so it will be the square root of p times q. Once again, this might look a little more familiar. When we dealt with binomial populations just last unit, we said that the standard error, sigma, was square root of n times p times q. Where's the n? Where's the n with the mean? Where's the n with the standard deviation? Well, keep in mind, proportions are fractions, and fractions get divided by n. And when they get divided by n, the n's will cancel themselves out. So these are the things that we need to focus on right here. All right, the mean is now the letter P, and the standard deviation is root PQ. So I'm going to leave those blanks there for a second, but let's just take a bunch of samples from this population, because that's what it's all about, taking a population and breaking it up into many samples. So we have 1, 2, 3, all the way down to, let's say, n samples. Okay, so instead of saying x bar, which is the sample mean, we use this letter instead, P. But it's about to rain today. I'm doing this video on Tuesday, and it's about to rain pretty soon, so let's give P a hat. I'm not joking. This is called P hat. I can't make these things up. All right, so P hat sub 1, P hat sub 2, P hat sub 3, all the way down to P hat sub n. And so now let me go back to up here. Well, let me do this first. This collection of p-hats, this collection of sample proportions is called a sampling distribution, sampling dist of proportions. I will actually spell out distribution. And we're going to find out some information. Instead of saying the generic if n is greater than 30, like we did with the central limit theorem yesterday, I'm going to say n times p hat is greater than or equal to 5, and n times q hat is also greater than or equal to 5. This is going to be how we're going to decide whether we get good samples here. So for the sampling distribution, samp dist of proportions, we can find the mean of the sampling distribution. And the mean of that sampling distribution is the same as the mean of the entire population, just like the central limit theorem yesterday. So if n times p hat is greater than or equal to 5, and n times q hat is greater than or equal to 5, we can find this right here. It could be found that the mean of the sampling distribution is equal to the population proportion. It could be found that the standard error, aka standard deviation of the sampling distribution, is equal to the square roots of p times q over the sample size. And this is not just something that has come out of nowhere. Think for means right here. So for means, the mean of the sampling distribution was equal to sigma over the square root of n. So now for proportions, that's going to be, well, sigma, what did we just learn sigma is? It's right here. So that would equal the square root of p times q over n, root n, I'm sorry, which would equal the square root of p times q over n. So I'm not just coming up with this out of thin air. This is built off of the sampling distribution of means, and I am simply converting these formulas to proportions for you. Okay, so for means, this was what it was, and then we're just using the proportion knowledge. So I boxed that on purpose. All right, next we're going to go over the big statement, and then I'm going to do one example, and then that's it. So I can't call this statement the central limit theorem because we're dealing with proportions here. The central limit theorem only deals with sampling distributions of means, but I might as well call it the central limit theorem. Here it is. If n times p hat greater than or equal to 5, and n times q hat greater than or equal to 5, the sampling, that's an S, the sampling distribution of proportions is approximately a normal distribution. And let me draw that normal distribution. The sampling distribution of proportions, so the collection of p hats, will be approximately normally distributed. And that means we could use z-scores, huzzah. And the z-score will look just like this, p hat minus u sub p hat divided by sigma sub p hat. All right, let's get to our one and only example for today. You could pause this video and look at it any time. So here we go. Find the probability that in 120 coin tosses of a fair coin, between 40% and 60% will be heads, inclusive. I'm going to underline that word inclusive. That's important. We're going to include 40% and we're going to include 60%. All righty then, let's get to it. So let's talk about our population first. So for our population, the mean, well, first off, it's a binomial population, right? You're flipping heads or tails, okay? The mean is p this time. Remember, mu, there's no mu, it's p. And what is p? It's 0.5. Standard deviation is root p times q, so root 0.5 times 0.5, which, by the way, is 0.5. Now let's talk about the sampling distribution. dist. What is our sample size here? It's a 120 coin tosses, so little n equals 120. So mu sub p hat is just equal to p, which is also 0.5. But here's what I do when dealing with proportions. Yes, it's 0.5. It's 1/2. But what I do is I convert the decimal into a fraction with little n on the bottom. So 0.5 would be 60 out of 120, correct? Yes. All right. Hold on, let me, correct. Yes, 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 you got me. Good. Let's now go to sigma sub p hat. That's going to be the square root of p times q over n. So that's 0.5 times 0.5 over 120. Round all your standard errors to 3 decimal places, standard deviation, standard errors, so 0.046. Ladies and gents, we have a mean, we have a standard deviation. I think we have all we need now to draw a normal curve and come up with a solution. So let me draw a normal curve. In the center, I'm going to put 60 out of 120. I need to do a little side work right now. What is 40% of 120? And what's 60% of 120? 40% of 120 turns out to be 48. 60% of 120 turns out to be 72. But remember, it's 48 out of 120, 72 out of 120. These are fractions. So I'm going to put 48 over 120 right here. I'm going to put 72 over 120 right here. Now comes the point in the lesson where people often give me moans and groans. Recall, we are answering a binomial question, because this is a binomial population, with a normal curve. Whenever we do that, here's the groans, we have to do a 0.5 adjustment. So if I want to include 40 and 60%, I'm actually going to start at 47.5 out of 120. And I'm actually going to go up to 72.5 out of 120. Oh, I'm going to shade the area that we're talking about right here. This is the area we need to find. From this point on, it's just a z-score question. All right, I'll find the z-score of 72.5. So I'll do z equals 72.5 over 120 minus 60 over 120 divided by 0.046, and I will get a z-score of 2.28. So this z-score here is 2.28. This z-score to the left is equidistant. It's negative 2.28. If you look up your z-table and you watch this, this is why I kind of like Zoom right now. I'll go down to 2.28. And where's 2.28? It is right here. Okay, so let me go back to my main screen. All right. It's 0.4887. So 0.4887 right here. 0.4887 right here. Picture's worth 1,000 words. Let's add these together. And I get my answer of 0.9774. So moral of this lesson, remember to use your data on the sampling distribution of proportions. And remember, you must do 0.5 adjustments on your fractions. I hope that this was useful. Ask any questions you have.